which are say single node jobs, which could be MPI or non-MPI for those of you who are familiar with HPC. But we have a large number of those. So you can have thousands or millions of those jobs which we need to run. So traditionally, those jobs were run in-premise, and we were limited by the infrastructure. We'll run them one after another in many cases, and so on. So the goal is really throughput rather than best performance of individual jobs. And the use cases are basically we want to do regression, functional testing, multiple realizations of these simulations in many cases. You can also think in terms of machine learning applications where you want to do kind of hyperparameter training and things like those, uncertainty and so on. We also use Kubernetes for another use case, which is sort of developing high-performance services using Kubernetes with replication and high availability. But in this talk, I'm really going to talk about how we use Kubernetes and in particular Google Kubernetes Engine GKE for elastic scaling. So quick thing about a particular case study which I'm going to talk here is about some of the oil production networks. So not computer networks, but essentially networks of pipelines. And so you have, say, 100 wells, and each of the well where oil is going to come up has certain parameters that can be adjusted. Right? So you can have pressures and temperatures and kind of the gas that you're going to inject into, so that your ultimate goal is to get more oil at cheaper costs, essentially. So then basically you have these sets of parameters and kind of becomes like an optimization problem. We have software such as Pipeman which can simulate those environments. But essentially in the graph here you kind of see like several wells on the edges, and then you have these sort of parameters which can be tuned. Right? So it kind of becomes like a very large sort of graph, and becomes like a network optimization problem. But what we can do is, since this is a very large network, if we solve it together, it can be very complex and time-consuming, but we can break it down into subnetworks and solve those subnetworks in parallel, and then kind of have a couple of iterations which kind of converges the solution. So in general, those sort of problems can be generalized into containerized simulations where we have create like an elastic simulation cluster with Kubernetes, and then we can run different types of simulation engines using that. Kind of going to skip this, but this is essentially some core architecture how we are doing this optimization in parallel. But in terms of some of the results that we get, so the blue line is the original sort of algorithm, and then the yellow is what we get when we are running with Kubernetes and Google Kubernetes Engine. It kind of scales very well as you increase the number of wells, and the problem is becoming more and more complex. So some of the features that we use from Google Kubernetes Engine and Kubernetes is node autoscaler. We use the job constructs. And for some of the high-performance services, of course, we use the rollout updates, health check, load balancing, and HPA as well. So in summary, Kubernetes is enabling us, in particular with GKE, with elastic scaling, and virtually sort of unlimited access to the latest hardware and resources that we need for scientific computing. The bottom line is kind of the Kubernetes enables oil and gas companies to deliver much needed energy resources to consumers with greater safety and lower cost. And so in general, I'm definitely interested to hear more about any open source or managed services that you may be aware which enable HPC for using Kubernetes. My time is up.
Hey everybody, my name is Sherry.
We get a new technical time. Okay.
My name is Sherry. I'm from Elastic. If you're familiar with Elasticsearch, we are the creator, developer, and maintainer of the Elastic Stack, or formerly known as the Ops Stack, of Elasticsearch, Logstash, and Kibana. We also added a Beats and PM to the family, so that kind of messed up on the moniker. I really like the Ops moniker. So in my talk today, we're going to talk a little bit about monitoring. So monitoring means different things to different people. So in this context, monitoring just means collecting, parsing, storing, visualizing, analyzing, act on the logs and metric events. That is coming from your application, from your services, from your community environment, just everything that runs within Kubernetes. So one thing to keep in mind, to have a good monitoring system, it has to be easy to maintain, it has to be reliable, it has to have some sort of defined lifecycle. So Kubernetes is great. It makes application development very easy. Application development with container very easy, but it poses a separate sets of challenges, different sets of challenges because it's ephemeral in nature and dynamic in nature. So you will have scale up your deployment, scale down your deployment, containers removed to a different pod with a different machine with a different node. So it poses a different sets of challenges. At the same time, your application developers still looking at logs or metrics, or perhaps container metrics. I feel like I'm talking as fast as I can. I think I am. And then your administrators obviously is looking for their infrastructure logs and services and metric events. And at the same time, they want everything. So I feel like the Elastic Stack has a unique place to help with all of those requirements. So are people familiar with the Elastic Stack, the Elasticsearch, the Ops Stack? Okay, I see about half. So I'll run through this as fast as I can. So at the heart of our stack is Elasticsearch, which essentially is a data store. It's based on the Lucene libraries, but it's very distributed. It's highly scalable, and it's not unusual for us to see customers who are running tens of terabytes of data per day for logs and metric events, and the eBay folks who give a talk at our meetup recently actually runs about a petabyte of data and metrics per day. And to ingest data into Elasticsearch, we have those two modules. One's called Beats, and the other one's called Logstash. So if Beats are typically for things like metric events and log events, and then Logstash is pretty much for inputs like you're sucking up events off your TCP port, your syslog, or something like that. And then on top of that, there's the Kibana, which is a visualization layer that just help you to explore data within the Elastic Store. And on top of that, we have a whole set of solutions for APM, metric, application search, business analytics, and security analytics. And we also provide our own hosting environment that could be deployed within the AWS infrastructure as well as the GCP infrastructure. All right, moving on. Let's talk about Elastic Stack and monitoring. So you could, with our Beats module, you could start shipping logs and metrics within minutes. And then you will have pre-built dashboards that get you up and running quickly. And in addition, that the Beats has what we call the auto discovery feature that lets you discover the different deployments that you have brought up, different services, different pods that has brought up, and automatically start shipping events and metrics into your data store and let you visualize those quickly. And logs and metrics lives together. And here's a typical architecture diagram of having, I don't know why this is not highlighted. There we go. Okay, so this is a typical architecture diagram. So we have file B runs as a data set or as a metric B as a data set. And the other, obviously, is actually run them together. And then here is just a diagram of what that looks like underneath. So essentially, the Beats module is listening onto your API services and deployments that's coming up. And then you have a separate module that basically suck up your metrics and log events and parses them. And then this is the feature specifying our auto discovery. Again, we use the very rich meta data that's available through your Kubernetes infrastructure. And then this is the comprehensive metric collection coming off. So you can see you are monitoring at the system level, at the deployment level, infrastructure level, pod level, node level, so everything you wanted to do there. All right, here is the sets of metadata. Oh, perfect. So jumping in to my demo. Okay. That bigger. Oops, that's, give me one sec. familiar with the guestbook application? Yeah, okay, perfect. That's what I'm gonna do. So I'm gonna go ahead and just deploy the guestbook. And then I haven't really changed. All right, okay, it's okay. All right, I got it. All right, I better hurry. Okay. Grab the next command. All right, so it looks like I'm up and running. So basically, essentially, it deploys the front end, and it has a little guest book, and the back end actually uses Stratus. And then I'm just going to go ahead and I'm just going to try to figure out what I expose the IP address for the guest book so I could get to it. So just, so I'm waiting for the external IP to be assigned. So I'm going to go ahead and grab the next command while we're waiting for that. While that is running, let me bring up my Kibana instance. So here is my Kibana discovery. So this, I have a Elasticsearch cluster running on off our Elastic Cloud Elasticsearch service system, and is off as you can see is off GCP. And let's see. So it looks like my front end is up and running. So I'm going to go ahead and fire up my file beat, and then I'm going to go ahead and fire up the rest of it. Alright, is it working my phone? Alright, cool. Get that fired off. Get the podium light on. Don't worry about the time. Alright, I'm gonna go fire off. So I fired off two things. All right, so fired off three things in a row. So I fired off the metric beat, the file beat, and also the packet beat. So what that means is that I'm start collecting all the log events that's coming off my Kubernetes deployment, as well as metric events, in addition to packet beat, which is all the packets that's been going in and out of my deployment. So I am going to go over here in my Kibana instance. So we have a dedicated UI just for logs. There we go. Okay, so as you can tell that my deployment is being shown here. So there's my Kubernetes. It looks like it's not running a whole lot. So I'm going to go ahead and go grab my guest book address. Here, Virtualizing Your Ci. Events. Let's do Sherry. Submit. So let's see. Finish that. So we have a dedicated UI just for the infrastructure here. And then currently it does not look like it's very busy or anything. And then we'll go to Kubernetes. Doesn't look like anything is happening right now. And then with the Docker events that's being generated. And I see a little bit events that's coming in. And I could go to view metrics here. And it's loading, so you can see there's a little bit of traffic going there. And then let's go to the dashboard quickly. I'll try to be as good as I can be. And there's some metric events, so I'm like running about 4 hosts here, and they're inbound traffic, outbound traffic, and all the traffic that's coming in, as well as the host overview. So there's I didn't much going on last. Oh, I get it. I changed that to last 15 minutes. There we go. So these are the container I'm currently running. One thing I love Kubernetes is just the amount of like containers, you will see all of a sudden that's not been brought up. It's shocking. All right. So, and then finally, one more thing. So you can see our logs coming in. Get rid of that. Get rid of that. Refresh that. Oops. So. There we go. So these are the logs that's coming in, and then following the log UI. There's some logs. Oh. Time's up. All right. Refresh that. There we go. There are the logs coming in. So
Can you reset the clock for time? Okay, start. Thank you, everybody. Capacity planning on public cloud is hard.
can you hear me?
Yeah.
Okay. Capacity planning on public cloud is hard because if we over provision, it's not as if we own the machines. You're paying for capacity that's running but not running any workloads. And if you under provision, then you have to worry about what kind of public cloud cost management tags do I need to use, and how does it tie into my cluster or scaling up? And if I want to scale down, who's going to drain my node of the pods that are running on the node? And what is the default size of my kubelet worker node? Should it be a CPU-intensive machine, a memory-intensive machine, etc.? And if we look at the capacity that's made available to us by public cloud providers, it's no longer a large server blade machine with large capacity that's uniform size. You get really small instances like 3 nano on AWS, all the way up to really large instances. And you no longer have to go and apply for a purchase order to procure a new machine to stick it into your Kubernetes cluster. You can get a new machine at that API. So is it possible to actually completely virtualize your worker nodes so that you're only paying for what you're using and not dragging along your manual capacity planning practices from on-premise to public cloud? So if you look at Kubernetes architecture, the notion of a kubelet worker node is coming from two processes running on your worker nodes. Virtual kubelet process and the CRI. So kubelet is receiving commands from the Kubernetes controller saying, hey, kubelet, run this pod, and kubelet offloads work to the container runtime interface, which talks to Docker by default, saying, hey, start this container, stop this container, pull this image, etc. So there are two ways of virtualizing your worker nodes by virtualizing either kubelet or CRI. So the first method is virtualizing kubelet. So let's go ahead and look at the demo to see how we can do that. So here I have a single EC2 instance that's running a very basic Kubernetes control plane with the API server, controller, scheduler, and I also have a virtual kubelet process that's pointing to AWS as the provider, and we have set the provider config to 5.0. So if you look at 5.0, I've set my region to US East 1, and I've also set a cluster name to virtual kubelet demo, and let's make a mental note of virtual kubelet demo here. At the end of the file, we've also configured a fake capacity. What we're saying is a fake worker node with this amount of CPU and memory and this pod limit, so that as far as the Kubernetes scheduler is concerned, it can schedule pods onto this virtual node.
So let's look at an Nginx deployment where we are asking for 3 replicas. And here is the virtual kubelet demo cluster that we configured on Fargate. And we see that there are no tasks that are running on this virtual kubelet cluster, on this Fargate cluster. So if we create the Nginx deployment, we see that the pods are in pending state. So what's happening is we are getting just-in-time provision infrastructure to run our pods on Fargate that has been configured with our virtual kubelet node. So if we look at our Fargate cluster, we see that all 3 pods are running as Fargate tasks on the virtual kubelet node. So if we delete the Nginx deployment, we should see that the Fargate tasks have disappeared. So you're getting just-in-time capacity that's only available when your pod is up and running, and it disappears once the pod terminates. So that's the first method of virtualizing your kubelet node. And the second method is virtualizing your CRI. So you have a regular kubelet node that is running the kubelet process, and instead of talking to Docker or Rocket as the CRI, you can talk to a virtual CRI called Kiot, which gives the notion of a very large capacity kubelet node for this worker node. So let's look at a demo of how that would work. Here I have a single worker node Kubernetes cluster with a master node and a worker node that is configured with Kiot as the CRI instead of the default Docker or Rocket or any other CRI. So if we look at the capacity of this worker node, it's advertising 124 cores, a very large amount of memory, and it's saying I can run 1K pods, which is actually not the case. It's actually running on a T3 medium instance. So it's not running on a large capacity node. So if we try to create the same Nginx deployment with 3 replicas, we see that the pods are in creating state. And if we look at EC2 console and I search for Nginx, we should see that there is just-in-time capacity that's provisioned for the pods that should come up in just a second. So what's happening is that the kubelet node has asked Kiot to start the pod, and Kiot talks to a nodeless scheduler called Milpa that will provision just-in-time capacity in shape of EC2 instances that will run your 1 pod per instance. So we see that our 3 pods are now running, and if we look at the tags associated with the pods, we see that we have very nice labels being translated to instance tags, so you can do interesting queries based on that. So here is the label that we have assigned for the deployment with app being set to Nginx. And again, once we delete the deployment, we should see that the underlying capacity disappears automatically. So the instances are being shut down. So is this the holy grail? We really need to provision a lot of, should we get rid of all of our worker nodes? The answer is no. With virtual kubelet, it's still in experimental state, and you cannot run stateful applications. And you can only ask for the kind of resources that your underlying provider supports. Like in case of Target, you can only ask for CPU and memory, and you can only ask for predefined amount of resources that your underlying provider gives for you. And with virtual CRI, it is production ready, and it still doesn't support stateful applications, but you can ask for any kind and any amount of resources. So the ideal scenario is a hybrid cluster with a couple of regular nodes and one virtual kubelet/CRI node that can eliminate a lot of the manual capacity and cost management needs for you. The takeaway is you don't have to drag along manual capacity planning practices through public cloud, and virtual kubelet, virtual CRI are emerging technologies that I highly encourage you to give it a shot. And Nodeless is a very clean cloud-native way of consuming Kubernetes. And here are a few resources. I'll upload the slide deck to the meetup page at the end of day 2, and please catch me for Q&A at the break. Thank you.
Whoa.
Hold on, don't say anything yet. Can we get 10 on the clock? And then I'll tell you to start. So go ahead and get comfy.
Hello.
You plug yourself up.
Oh.
So let's wait for the screen. It'll take a couple minutes. There you go.
Good.
And you ready?
Sure.
All right, let's start.
All right, guys. I'm filling in for somebody here, so I just put this together. So I've got some fun stuff. My name is Chris Fregley here. Let me maximize this. I see like a lot of familiar faces. I run the Advanced Spark TensorFlow meetup. I think it's probably the longest running TensorFlow meetup in the Bay Area. So if you're not part of it, yeah, check it out. Come on by. We've got a couple coming up throughout the springtime here. Former Netflix, former Databricks. So I created this company called Pipeline.ai, and I want to highlight how we use Kubernetes. We chose Kubernetes pretty early on. I'm actually wearing my Seattle KubeCon 2016 shirt, which I've kind of gained about 20 pounds since then, so it's a little tight. But shows that like we were part of this community pretty early on. Pipeline's part of the CNCF. We actually use Rook and Ceph and a whole bunch of other stuff. So like today's blurb here, I think I have 5 or 10 minutes. We'll shoot for 7.5 maybe. I've got a demo as well too, but yeah, so you could try the pipeline stuff as well. Kube has been absolutely crucial. I'm the kind of guy, I tried to get Mesos to work about 2015, and I couldn't install it on my local machine, and I just gave up. And actually, the same thing kind of happened with Kubernetes early on, but I stuck with it. It was a little bit more friendly. There were less C errors like showing up in system libraries and things. So we made the right choice, and I want to highlight, oh yes, we also use Istio, which I believe is also a CNCF project. Istio has been absolutely crucial because we're very focused on really putting machine learning into production and being able to route traffic and do A/B tests, do shadow mode, all that kind of stuff. So the problem here is, I call this real-time machine learning. It's really, at Netflix, we would push models into production within probably minutes, and we could compare them and actually validate these models in production and not do them offline and hope that this model is going to work in production. So really taking some of those learnings, I was really frustrated when I was working with Databricks where all of our customers were still doing batch. And I mean, this was 2016 when I was at Databricks, and it was like, come on, guys, we have to get with the program here and start to get these models into production quicker. There's this famous blog post called Uber Michelangelo, came out in 2017, I believe, September, that really highlights the problem. The actual first sort of well-known documented version of this problem is the Google paper called Machine Learning High Interest Credit Card of Tech Debt. So that's a very famous one. We actually are constantly fundraising for Pipeline, and it seems like the VCs all seem to know these two papers. In fact, they've been hounding the creators of Uber Michelangelo to leave and start a company, which they actually just did. Yeah, also others we've been working with, Comcast, Pinterest has a really good machine learning platform that they're like open sourcing, supposedly. Hopefully we get to see that. So some of you might be familiar with Amazon SageMaker or Google Cloud ML or like Azure ML. The problem here is all these have specific sort of batch-oriented type of focus, and to really make them continuous and get models into production, you have to stitch together like 9 different Amazon services. There's some here I've never even heard of, like Glue and yeah, Fargate. I don't really know even what Fargate is, but I think it's yeah, I don't know. Yeah, so she was just talking about it. I still don't know. So here's kind of, yeah, let me zoom in here. So we're, oh, that was the wrong kind of zoom. We're Kubernetes native. So here's an example where we're actually generating 11 different variations of one model and across different runtimes, and we're able to push these into production and compare them. And that's actually my demo here has one model, the MNIST model, where we're recognizing handwritten digits. And we've got 4 or 5 versions across different runtimes, different frameworks, and even on different clouds. So because of Kubernetes, we can actually run across Azure, Google, and Amazon. And also one metric that you'll see here is cost per prediction. I don't really know how to max, well, I'm going to put it in present mode. So cost per prediction, this is actually in real time, how much is each prediction costing, right? And we've kind of inflated the numbers, otherwise these are really close to 0. You wouldn't see them, we'd have to have really long digits there. But this is, depending on where they're placed, what kind of instance they've been placed on, this is telling me how much is this inference rightly costing. So the sort of interesting thing about machine learning in production is the actual jobs, might take 8 hours, 24 hours, 2 weeks, but these models live in production for weeks and months sometimes. And if you can do small little microsecond savings for each prediction, that actually adds up, especially over a couple months or the full life of the model. This is something else too where you could actually deploy, so like we use something called Jupyter Lab, which is a pretty thick skin on top of Jupyter. It's championed by the Bloomberg folks, so there's a huge community. It's kind of the next generation Jupyter, like notebook, and we've actually started hooking into it where you can just right click on your model, deploy it to Pipeline, and then it goes out to all. And we support all the different models, of course. So here's a bunch of links. If you guys want to take a quick snapshot, basically blog.pipeline, slides.pipeline, meetup.pipeline, YouTube pipeline. We have a million different. We've got about 3 years of material out there from the Pipeline meetup, or the Advanced Spark TensorFlow meetup. And then quick start. If you actually want to get this running in your EKS cluster or any on-prem cluster, all we require is that you point us to your Kubernetes cluster and we'll deploy everything. Including Istio, including the distributed file system through Rook and Ceph. So how much time do I have? Oh, perfect. Yeah, so I just did a blog post last week. I do this monthly call, dev community call, which is all posted on YouTube. It was called Slack After Dark. So a few years ago when I was with Databricks, I created something called Spark After Dark. It rhymed a little better, where we built a dating site with Spark. And I've extended that kind of loosely to call Slack After Dark. We have a fancy logo and everything, where it's a dating site within Slack. So you could actually do / swipe left / swipe right. We, right now, by default, match engineers with non-engineers, just to be silly. So let me show you guys what we got going on. So if you go to blog.pipeline.ai, you'll get forward to the Medium article. It's about a 5-minute read, but I'm most proud of the logos and stuff. SAD is the acronym for Slack After Dark. As a repeat customer of like online dating sites, it's very, very like close to my heart. And this also came out around like Valentine's Day as well too. So my friend Ancha she was brave enough to actually participate in this. So we You would log in with your name, or sorry, a picture of yourself, which she chose off of her GitHub. And it'll tell you right away whether or not we predict that you're like an engineer or non-engineer. This is totally like not the best idea, by the way, but which is why, yeah. So, but if you have a good sense of humor, go there. So she's obviously an engineer. If you see the picture here in a bit, you'll see she's wearing a Docker shirt. So, and right off the bat, she matched with Ehrlich from Silicon Valley. There's a, yeah, he's an engineer, but he kind of, yeah, doesn't really like that part of his life. So that was pretty funny. It sort of inspired us to keep going. So this is the actual overall architecture here. When you do like a /predict, for example, or /match, it's actually going back. It's going through Istio. If you noticed, I think I skipped over it, but we actually have an ensemble of models. So one model, version 1, said she's a non-engineer. The second model that was trained with more data said she certainly is an engineer. And I actually start with the prediction side of things in this blog post, and then I go to the online training part. So this is also how we can route traffic through Slack. That goes back to pipeline. It's basically calling pipeline APIs, right? Like REST APIs. So let's see. So here's the training side. So the first version of the model was really bad, said non-engineer. So like we decided to actually fix that and fix the model and introduce new label data. Now this isn't, this is totally overfitting on this image, we understand, but it's a fun demo. So we take that exact same image, we label it as engineer. That then triggers a training job off of Kafka, and we have a better model. So, yep, so check it out. Thank you.
All right, so hi everyone. Hi everyone, this is Ayush Paderia from Mercari. I work as an SRE at this company, Mercari. And the title of my talk